Um, let's see. So, welcome everyone. Kelly Roos is my name. I'm at a little place in the Midwest called Bradley University. I'm a physicist, of course, by training, and I've taught at Bradley for a long time. I don't know if I should tell you the exact number, or I might be thrust into some kind of midlife crisis. All right. So I started teaching before the advent of the Pentium processor. That might give you a sense. All right. And so I've tried a lot of things over the years. And specifically, I'm referring to integrating computation into my courses. I started out in the upper level courses and really statistical mechanics, which was a playground for this kind of thing. And somewhere in the neighborhood of the year 2000 or so, maybe more like 2003, 4, I started integrating computation into the introductory courses. And I've tried a lot of things, and I've been too ambitious, and I also, on the other end, I've erred by not expecting too much of the students. And so all I'm going to do is pour forth any little bit of wisdom I have for this tonight. All right. And like I said, I'm happy to interact with anybody outside of this as you feel I have anything to offer. All right. So let's get started. I'm going to start out and I'm going to share the screen. And once again, every once in a while, I might stop sharing or try to look back at the to make sure I'm still going. If something happens and I seem to be talking without sound, for sure unmute and yell at me, okay? So let's do this. Oh, somebody's coming in. Hold on. Let me let them in first. Okay, so I'm going to share, and now you should see all of yourselves, and I'm going to go to some slides. All right. And you should see a slideshow started. Okay, so I'm going to start here, and I'm going to describe what I do or did. It's been a little while since I've taught the intro calc-based class, but I'm going to give you a description of what I ended up doing after about 10 years of implementing things. And so I'm going to warn you at the start, the list I'm going to produce here is what I did sort of the last couple years after trying a whole bunch of things. And just a warning, it's going to look very ambitious, and I would not recommend that anybody just implement this outright. The place to start, as with anything, is to start with small, bite-sized activities, and it's always best to start simple and then build curricularly as you go along and as you observe how the students respond, and learning how to assess things, that sort of thing. So it's always good not to just jump in with so this is going to look ambitious, right? So, but I'm going to show you the possibilities and what I've developed. Now, first of all, this is a list. I'm going to show you what I have done. And keep in mind, as I have indicated here in the parentheses, this has been implemented mostly during lab meeting times. I always had the luxury of 3 hours a week of lab time. And it was a perfect place to start implementing computation. There were a couple other favorable situations, not only the amount of time per week, but at the time I was doing all of the sections of the introductory mechanics. And if I wasn't, I usually had somebody who was willing to come along and do the same things. So we were able to keep a uniform experience for the students. All right. So those were two things I had going for me when I started doing this. The other thing, one of the reasons I started doing this also was, and again, this is maybe getting close to 20 years ago, I was fed up with the way those intro labs in mechanics went. Those cookbook labs where you have students try to do a lab write-up. I just very, very quickly, after about a decade of teaching, completely soured on the educational value of those cookbook labs that we have the students do. So I started implementing computation to liven things up, right? So that was the situation. And so I'm going to start listing things. Now, you'll see a topic here in this list And you'll also see a in parentheses here, HW, of course, means homework. And then in bold at the end, this is essentially what the activity is. And in this case, I call it the kinematic equation solver. Mainly homework is where this was implemented. And I just had the students evaluate a function, the kinematic equations. All right. So that's where I started. Now, I actually didn't quite start there when I started doing this. Here's where I actually started. So look at number 2 on the list for a moment here. All right. And I call it the ball drop experiment. In our lab, we either did a basketball and or a beach ball. And this was the good old classic measuring G experiment that you do at the beginning of a semester. If you drop a basketball, I used this was in the context of using a motion detector. And even a basketball gives something less than 9.8 meters per second squared. A beach ball gives much less. And then it provides the opportunity for students to realize that we have to account for something else. And of course, that something is air resistance. So this is where I started, actually. And I started with spreadsheets. I would have them do the lab, do the actual experiment. Then I would have them do a spreadsheet model, including air resistance, which was proportional to V, right? Just proportional to V. The damping coefficient, right? The proportionality constant to V in the damping term is what we would then vary, and they could use that as sort of a fitting parameter to match their experimental data. And then I would also have them do the actual integral, right? And that's the homework part here. So I did a lab. I integrated with the lab a computational model of the drag force, and we used the simple Euler method to solve the differential equation. And then I would make them do the actual integral as a homework assignment, which you probably experienced the abject horror that most introductory students have when they're forced to do an integral in a physics class. And so, yes, I made them do all three. So I tried from the start to integrate lab, experiment, computation, and the analytical, non-computational based theory. All right. And so that was where I started, but it became obvious that even with a spreadsheet, now this is back a while back, 15 to 17 years ago, the students at the time really weren't very familiar with spreadsheets. To be honest, they weren't familiar with much at all computationally. And so it became obvious I better spend some time getting them up to speed with spreadsheets. That's when I implemented this equation, kinematic equation solver. All right. That was entirely for two reasons, really. And I'm going to demonstrate a little bit of this coming up for you. But this is just evaluating the functions in a spreadsheet. I call it a kinematic equation solver because I wanted them to use it. I wanted them not to just build it and see what you could do with a spreadsheet. I wanted them to get into it because if they don't use it and don't use it often, it don't stick. So this was sort of some training, I guess you could say, via homework. You got to make them do it to get them into the spreadsheet such that when they get to the modeling stuff here, they're not stumbling over the tool as much as the actual method, all right? So that's where I started, and I spent years doing this and trying to perfect the approach and just playing and seeing what the students could do. Okay, I'm going to stop sharing for a moment. All right, and go back and let someone in. Looks like I'm still with everybody, right? Okay. Okay, back to the presentation here then. And I think it's still going. Good. All right, so then and remember now, this is being done in the labs, all right? One thing that I already communicated, I was kind of fed up with what I perceived as poor educational value of the labs, and so I implemented other things right into the instead of labs. One thing over the years, a protest that I get, well, not so much a protest, but a question, is if you're going to implement computation, especially in an introductory course, doesn't something have to go? And then it's usually followed up with, well, what has to go? The answer to the first question is a resounding yes, and I'm not going to try to hide it or sugarcoat it or anything like that. If you do this kind of thing, integrate these computational activities in an introductory course, a lot does indeed have to go. And if you're in the camp, in the traditional camp that says we got to cover the traditional canon, this might not be for you, all right, because stuff does indeed have to go. And so the question is, what has to go? I came to grips with that question early on, and I've already told you the answer. For me, it was just scrapping most of those worthless lab exercises. I still try to do labs, by the way. I still try to integrate as much as I can the lab exercises, doing something in the lab with the computational stuff, right? But that's the answer to that question. Something does indeed have to go. And that I don't have any great wisdom for you. We could talk about it a little bit if you wanted to, and discuss what you think is important and what's not. I'm of the opinion that more is not necessarily better, as long as you're going in depth and teaching the students how to learn this stuff. That's a very nebulous way to state it, but I believe that. All right, so I do something called a falling sphere. This is followed up right after the ball drop experiment, and it actually makes the model a little more realistic, because here we're able to use the version of a drag force that's used in wind tunnel experiments that the engineers do. And so I basically start out by saying, how long would it take a basketball, if you dropped it from the observation deck of the Sears Tower, how long would it take to hit the pavement? We go around the room and they offer guesses, and then we build the model. Right now, if you thought they were freaked out about doing this integral proportional to V, they are really freaked out, even though you can do it. All right. And
hey, Kelly, I'm sorry.
Yeah, go ahead. Go right ahead.
Did you mean to share your screen? Because I don't see it.
Oh, did I not? Oh, I forgot to share again. Hold on. I'm glad you called time out there. Okay, I should be sharing again. And the only thing you missed is the third bulleted point falling sphere. Right? So I stick that in as another model to build. All right. Then we do a Saturn V launch. By the way, the falling sphere and the Saturn V, this is just a modeling the launch of a Saturn V, not following through and trying to get it to the moon. All right. And I can tell you a little more about this. But
hi, Kelly. Just to make sure you're not showing anything right now.
Really?
I just see a picture of you. There we go. Okay. All right. Sorry.
Can you see it now, everybody? Okay, now. If not, unmute and holler. All right. I'm assuming everybody see. Sorry about that. I don't quite know. You know, this online stuff has a mind of its own. I'm convinced that there's a witch doctor down in New Orleans with a little computer sticking it with a pen right now. Right. I know that was a poor attempt at humor. I probably got some more you're not going to like. All right. So I implement things that, because most of the students in our intro calc-based classes are engineers. And I try to implement something that smacks of a design issue. Right. And so the Saturn V launch does that, and it beats that one of those, again, what I call worthless intro mechanics experiments. Right. Then and I tried to implement this. This is a good, I think, the two-body gravitational orbit problem. This is just simple modeling the Earth going around the moon with simple Euler-Kromer now. We've modified the Euler method. And this plays, I think, a good role for intro students in learning about gravitation. You know, that gravitation chapter, I'm not so sure just having them calculate the the attractive force of them and their Aunt Helen is that valuable. Whereas here we actually build a model using the only thing is the attractive force of gravity. You do it Euler-Kromer and elliptical orbits just pop out, right? You can even delve into all of Kepler's laws with this. It becomes a little bit of an experiment then. I call it the gravitational lab, right? Finally, toward the end of the semester, we do a simple harmonic oscillator. as well as a damped-driven harmonic oscillator. I like to do the very last one in the mechanics classes because it opens up the possibility for resonance. Resonance is too important of a concept to tell the students, in my humble opinion. You're not supposed to understand this yet because the mathematics is too hard. So come back in 2 years in your mechanics, your Newtonian mechanics class, and we'll teach you all about it. Whereas here, with a simple Euler-Kromer method of solving the differential equation, which even intro algebra students can do, because all it is a linear equation you're solving over and over again. The whole concept of resonance just pops out, right? So again, I didn't do this all at once, and you're looking at a pretty ambitious program here. And I only did this for a couple of years before I stopped teaching the intro calc courses. But throughout the years, I would implement some of these pieces of them and most of them, and then it sort of culminated in this. And this provides a story for the students, and it gets them up to speed to continue, if they happen to continue, for instance, with me into the second semester E&M. All right. So that's the list. I know some of you, in filling out that little survey, asked about what it might look like doing this in the introductory courses. Any one of these could be a sufficient amount starting out, and maybe that would be completely sufficient for your situation. You don't have to do this big curricular effort like this, right? Now, I do have all of these implemented in a spreadsheet, and I'm happy to share that with you. So remember, we're recording this. Also, I've got the slides if you want those for whatever reason, and also I have all the, and I'll show you where I'm going to share these implementations for all these things, all right? Before we actually build something in a spreadsheet then, and before we take a break to open it up maybe for some questions, I'm just going to elaborate very quickly on the 2 slides. If you were part of that webinar we did, it's been a couple weeks now, I flew through these because it's really one of the most challenging things a physics professor ever has is to try to give a talk in 5 minutes. That's just almost impossible, right? So I'm just going to elaborate a little bit because I flew through there. So why spreadsheets? And some of you asked, some of you are struggling with, do I do spreadsheets versus starting with a programming language? This is just my perspective, all right? Why spreadsheets? First of all, they're used everywhere. And they're available everywhere, free. And of course, if you have a Mac or a Windows box, then probably it has Excel. So I put kind of free, although it's really not free. These other versions are certainly free. So, but by used everywhere also mean that it is a good marketable skill to have. And I interact with a lot of professional, it's a long story why I do, but I interact with a lot of professional engineers quite often, actually, in some of the bigger companies, Caterpillar, Siemens, General Electric. And to a person, the spreadsheet is almost ubiquitously, almost daily used. All right. And so it's something that students should know how to step around in. Right. Let's see, I think it's a good level for interacting with a computer. When you just start with a programming language, especially with current students who really don't, very, very likely will not have any programming language experience whatsoever. And so if you start with a language, it's what I've found, you're sending them into a world of commands that are very nebulous at best. Some commands have some kind of meaning, some don't, but very seldom are the students guided when they're just starting out even to look at the numbers themselves, all right? And one thing that is very important for students, intro students especially, to understand that the computer isn't doing anything for them that you don't tell them to do. And moreover, it doesn't even do much other than represent numbers. Now, in many instances, the computer is very good at representing numbers, but there are cases and it's not hard to get to them, where you realize the computer isn't doing a very good job of representing these numbers, especially when it comes to arithmetic processes, right? And so the spreadsheet puts it out in front of them to view and interact with from the start. They're representing numbers from the very start, and I think that it takes the mystery out of a lot of what we want the computer to do for us. All right, so I think it's a good level for interacting with a computer. Also, and I don't use this solely, all right, but I use it as a transition to programming language. I sometimes use the term on-ramp for Python, MATLAB, C, whatever. My institution, we have a big engineering college, so MATLAB is the chosen computational environment that we use. All right, so I use it for an on-ramp. I want the students to learn the spreadsheet itself, but I also want to get them into MATLAB, at least some basic MATLAB, building some basic things in MATLAB. And so that's what I have used. And I don't have anything but anecdotal evidence that it's effective. All right, but I've noticed students don't fear a spreadsheet like they do if you just start with MATLAB. And I'm going to demonstrate this for you when we start building something. There's a visual one-to-one correspondence with the components of a programming language, right? And I'll show you what I mean by that. But there are colleagues of mine, friends across the fruited plain, who flatly disagree with my approach. They say, "Why do you need the middleman, sort of? Why do you need this on-ramp, this spreadsheet on-ramp as a transition?" One of the answers, of course, is I think it's very important to learn a spreadsheet. That we have students, especially in the age where most of our graduates are not going on to grad school. I think it's very important that they have spreadsheet skills. The second one is I'm not convinced that most of the ones that argue that they don't see a need for this spreadsheet, the vast majority of those will introduce their students to programming languages by providing them with partially working code. And I'm not convinced that the students learn really to do things from scratch. Now, it depends on your learning goals and your pedagogical intentions. It might be that you don't want your students ever to get things from scratch, but I can, within about 3 or 4 weeks, I can have students programming MATLAB models from scratch with this approach. All right, so do you need it? No, and I'm not going to argue that you need it. I won't have any religious arguments about this. It's worked for me, and I can demonstrate that it works. All right, is it the only way? No, absolutely not. It's also possible to very, very beneficial or useful for visually building algorithms. And I'm going to demonstrate this too. Finally, there's a lot of functionality. Again, I don't know that any of us would be too interested in using hundreds of thousands of rows in a spreadsheet. But I have seen some pretty serious data analysis being done at Siemens, for instance, in their medical imaging division. And these folks are using thousands and thousands of rows in their models in a spreadsheet, right? So it's not unheard of. If you're going to do billions, you can't do it. And if you're going to do serious number crunching, you're not going to use a spreadsheet, of course. Part of the reason I try to get my students into MATLAB as soon as I can, right? So let me stop sharing for a moment here. And let's take just a little bit. Let's go back. Let me go back so I can see you. So I'm not sharing now, correct? Okay, so let's open it up a little bit. Again, I'd like to kind of keep it moving, but let's open it up for a little bit of questions or comments if you have any.
So quick question. When do you start MATLAB? So you start off with spreadsheets, but what activity? Is it the last activity they do that you start introducing MATLAB, or is it, or do you gradually add it in with each of those activities?
Good question. When I was doing the intro physics course, I would do MATLAB towards the back end of the semester. I would sort of hint at it and show the students a code that was doing the exact same they just had their spreadsheet do. But I would put it in, and I used it just as I showed you on that last slide. I used the spreadsheet as a guide. I guess I didn't show that. Well, okay, let's not take time and look at it. by having them build the spreadsheet model first, for instance, they know what the results are, and they've already had the opportunity to investigate the accuracy of the model, so that when they start using loops and arrays and things in the programming language, and they get something out of it, they make their first graphs, they know what to expect, and so if they see nonsense, they know it's that they've made a mistake, right? So the short answer is I do it toward the end of the semester. What I would try to do, by the way, is carry it into the second semester, all right? Now, that's pretty ambitious for intro students. I admit, that's pretty ambitious. Now I teach it's essentially a sophomore, junior numerical methods class. I take the same approach, but I get them, they are doing their program, and some of these students have never programmed anything, by the way. And in this case, they're a little more sophisticated than, of course, freshman students. But they're programming from scratch with this guided activity I call the spreadsheet a guide. They're doing programs from scratch after about 4 weeks. Right? So the short answer is as soon as possible, but it's pretty ambitious to get freshman mechanics students into that. All right, but I about halfway through, really.
Kelly, Mark Jensen here.
Mark, how you doing?
I must admit, it's been decades since I had a numerical analysis class.
Uh-huh.
But they were always dead set against using anything with Euler's method.
Really?
How have you found the accuracy of that?
Well, I'm glad you asked. I'm going to be demonstrating this, and we're going to be working on this together. So I'll show you exactly. I leave it to the students to investigate this first and foremost. All right, because I try to instill in them a paranoia about their computational solutions. It's the same paranoia they should have about their analytical solutions, by the way. I mean, if students trying to calculate how far a ball falls in a gravitational field close to the Earth over 10 meters and they get 3 hours for the answer, they better darn well be paranoid about that, right? And so, so I try to instill the same paranoia for that. So now, one thing, Mark, if you're talking years ago, you know, we didn't have the luxury of these really fast silicon units we live with now. I mean, think of the power. NASA dreamed of the power that our students have their nose in. Those little square boxes they live with their noses in, right? And so back then, the Euler method was just too doggone slow. That was part of the problem. And to get an accurate solution, then you had to make your delta t so doggone small, it was impossible to get a tenable solution out. And so you had to rely on these higher order algorithms. Now it's not the case. I can do billions and billions of iterations doggone near instantaneously with the simple Euler. And I can investigate the accuracy, and as long as it's accurate and stable, that's another thing we have to consider. The fancy word is symplectic, by the way. As long as it's stable, accurate, then I don't see anything wrong whatsoever with using the most simplest way of solving the differential equation. Well, stay tuned. We're going to work through that. Okay.
Yep.
All right. Anything else? Any other concerns? Anybody blatantly disagree with my approach? It's okay. You know, being involved in the pickup organization, you have to have thick skin. Almost every workshop we do, people say, well, I wouldn't have done it like that. Why'd you do it like that? All right. Well, let's move on. So one thing, and I probably should have showed this already. Let me show it next. So, let me share. Let's make sure I'm sharing here. I almost made the same mistake. All right. So back to sharing now, and I'm going to go back to show one slide real quick. Then we're going to go to the spreadsheet. All right. So somebody unmute and tell me, can you see that same slide I just ended with?
Yes.
Yep.
Okay, good. All right. So here's the next one, and I've really already said what I need to say about this one, I guess. I call this the Rus Excel to, you can see XXX here, where XXX is whatever programming language you're trying to get to. All right. So I also have, I'm trying to come up with quotes that'll make me famous someday. So I don't know if this Excel to MATLAB method will ever be famous, or if anybody will ever quote me saying, coining the term live pseudocode. That's what I see the spreadsheet as. All right. It's something that is a good guide that helps students understand algorithms. All right. So I've already mentioned this, that this is my approach. I build a model together with students in Excel. The student's mission then is to take that, use it as what I call a guide to produce the Python or MATLAB or whatever version it is you're wanting them to get into. All right. They already have a working knowledge of Excel. We've done this many times. And as I've already said, after about 3 or 4 of these guided activities, they can pretty much produce from scratch the models they need to produce. Here are what I think are the benefits. All right. I've already mentioned it's a visual guide, and I've already mentioned that it has the students avoid having to code from scratch when they're just beginning. All right. So, but I think maybe it was on the last slide, one thing I want to emphasize. So the functionality aspect of it. What I'm going to do, let's fire up a spreadsheet, and I'm going to introduce what I call the control panel. All right. So that's, I think, is a very useful tool that one can do in a spreadsheet. And so let's do that. So I'm going to stop sharing. And if you haven't already, fire up a spreadsheet. Now, so I'm going to go back to sharing. I guess I should have stayed sharing, but I'm going to share once again my screen, and now you're going to see me sharing a blank spreadsheet. All right. All right. Now, unfortunately, I run a Linux box. I gave up on Microsoft and Mac a long time ago. And again, I don't want to engage in any religious discussions. I'm perfectly happy to talk Microsoft and Macs. All right. It's just I like free software. That's part of the reason, right? So, so I'm running LibreOffice, and whereas the functionality is the same, if you're doing this in either Google Sheets or a spreadsheet, Excel, it's going to look slightly different, all right? And I apologize that I don't have the Excel that you can watch, but I think it's going to work. And moreover, I'm going to sort of do this rather quickly, and it's probably not going to be too valuable to stop if you get stuck or something. Again, we're recording this, and I'm going to go slow enough that when you watch the recording, you can go back and probably figure it out. It does indeed look a lot like what Excel looks like. It's just not perfectly matching what Excel is doing, right? So if you end up getting stuck or you're not sure about something, I think it's probably more valuable to watch what I'm doing and then look back on the recording. And remember, I've also offered I can do this one-on-one with you anytime if you're interested. Okay. All right. So let's zoom in so you can see what I'm doing. All right. And so this is how to build what I call a control panel. And what I think we'll do just real quick is build this kinematic equation solver. All right. And that, I think, will demonstrate exactly what the control panel will do for us and your students. All right. So what I'm going to do in column A here, all right, I'm going to make a list of all the parameters. All right. So in the spreadsheet world, in the business world, I guess, variables are called names. Right? It's just the terminology. So I'm going to define a column, a list of parameters that are going to be constants. And these are the constants that would show up in the kinematic equations, for instance. All right. In the business world, they would call these names. You could also call them variables if you want. These are going to be constants that we're going to define. All right. So what do we need? We would need an initial position. All right. And so all I'm doing now is using text to define these constants that I'm going to use in the calculations. And I'm just putting them in a list here in column A. We would also need an acceleration. And so very first, as I'm doing this, by the way, remember I said when I take students through spreadsheets and get them using spreadsheets, I always try as hard as I can to make a one-to-one correspondence with what they'll be doing in an actual programming language. All right. And so, for instance, I'm going to have a constant called the initial position, a constant called the initial velocity, and an acceleration. And just naming things is an important procedure that the students need to learn to do. If you're going to have an initial position, don't call it your Aunt Helen or something like that, all right? That would be silly. So you want to have names that are meaningful. And so you could just call it A, but I like to spell it out. Accel is short for acceleration, right? This will probably do it for our kinematic equations, I think, right? Okay. Now, so that is the list. So those are the labels, all right? Now, adjacent to that in column B, adjacent to each one of these, we're going to do something special. And here's where we build this special functionality called the control panel. All right. Now, the easiest way to do this is to highlight the box, which is B1. That's right adjacent to x_0, or our initial position. Right. And everybody see, I'm going to move my arrow up to this little thing. Now, the same thing happens on mine as it happens in Excel. You see it says name box there? All right. I'm going to highlight that, and I'm going to type in there the exact same thing as I have in the box adjacent to it in A1. Now, it's kind of small. Hopefully you can see that. I typed into that name box x_0, and then I'm going to hit enter before I click anything else. The enter gets it sealed. All right. Enter seals it into the spreadsheet. Okay. Now, by the way, there is another place where you can do this. You don't have to use that name box. If you're doing LibreOffice, it shows up, I think, under data, all right? And it's called define range. You just have to get used to the spreadsheet nomenclature, all right? And in here, I could define a name or a parameter, constant parameter. It's the same thing. That's what name means. And then I could tell it where the associated values are going to be for that. Okay, I'm not going to use that here for this. We're going to keep using this little name box. All right. In Excel, it's called the name manager. And if your computer's set up properly, I think you can hit F3 and get to it. All right. But I like using this little name box because it's quick and easy, and you can do it really quickly. All right. So now, before we do anything else, let's put a number in there. Now, usually we start out initial positions at 0, right? Let's just call it something else. I don't know, 58. Right? I'm in the mood for an initial position of 58. Okay. Now, somewhere else in the spreadsheet, all right? Doesn't matter where. I'm just going to choose this box. All right. And let's do the following. Okay. So again, I'm going to do this kind of fast, but it's going to be sufficiently slow for the recording that you can go back and stop it and see exactly what I'm doing. I'm going to put equal sign. Now, here's where we have to make it clear to students. If students start with a programming language and the certain lines look a heck of a lot like a mathematical equation, don't they? Right? But you've got to bring to bear to the students and get it in their heads that equal sign does not mean identically equal in a computational environment in software like this. Equal sign means assigning. All right. So I'm assigning this box. What am I going to assign this box? I'm going to assign this box the constant x_0. All right. Now, Excel is much better at this than LibreOffice. If you're doing this in Excel and you type that in, you'll also see I don't know if you can see this. There's a little thing that says x_0. LibreOffice knows that I have defined a constant called x_0. In Excel, it actually puts it actually color codes the box which has the value in it. And then if you hit enter, it actually knows what the x_0 constant is, and it pops it where I assigned it to be that value. right? And you can do this anywhere. For instance, I can do it down here. Equals x underscore 0. All right. Equals x underscore 0, and so on. So it knows exactly, the spreadsheet knows that constant, and it knows the value that's stored there. Okay. And now you can talk to the students about memory storage, about random access memory, that certain values are stored in certain locations. Now, in a programming language, that is a very ambiguous concept. Stored where? Here, at least, you have a visual location you can bring to bear and say, now, this box is representing somewhere down in the recesses of your random access memory, and it's representing a number 58 with a combination of transistors, right? And, you know, I think it brings to life everything we want the students to understand about a programming language, all right? Now, here's why I call it a control panel. Go back up here. Let's say I don't want the initial position to be 58. What if I wanted it to be 21, right? Now, when I hit enter, watch what happens. It instantaneously changes everywhere, that parameter, right? And now I can program that constant parameter into any equation that I want to assign to any of the boxes anywhere in the spreadsheet, all right? So everybody see how that works? Okay. Hopefully you're able to do this along with me. Once again, I'm going fast, and I just don't think it'd be productive to really stop and take a long time to share screens and make sure you've got, so do your best to stay up with it. But I think watching it will enable you to do this on your own. And, you know, after we're done tonight, I would encourage you, and that's why I tell the students, as soon as you can, do it cold. Don't use the video as a cheat. Just try to do it on your own. That way it gets in. All right. So let's erase these. You just highlight everything, hit the delete button, and they go away. All right. Now let's complete our control panel here. In other words, highlight the box adjacent now to V0. Remember the procedure. Go up to the name box, or you could go to the name manager or the range, defining ranges in whatever free version you're using. Right, so I'm going to now go up to the name box, highlight it, and type in exactly what the label in the adjacent box is, V underscore 0. See, and then hit enter. Make sure you hit enter. If you use exactly what is in the label column, then you're never confused about what that number is actually representing. So here, 21 is associated with X0. I just defined V0. By the way, if you click somewhere else and then click back on the box you just defined, it still is in the name box. See that? V underscore 0. So it knows the memory location of any values associated with V0. Okay. And let's just start at 0. All right. We can call it 0. We can always change these numbers if we want to. And then finally, an acceleration here. Well, we have to define the constant first. So highlight in the B column, highlight the box adjacent to X cell. Go up to the name box, type in exactly as it appears in the label, hit enter. Don't forget that enter. That's an important step. And now this box, whatever value, will forever be associated with X cell. Okay, if we're close to the surface of the Earth, we could call this, if you want to get technical, 9.81 or something like that, right? Okay, so that is the control panel. And once again, you can go to any boxes here, and I'm just going to, in succession, define 3 rows, succeeding rows here, as X0, V0, and acceleration. And equal means assign. And let's just do a check to make sure I did it right. Good. Next one is V0. And finally, I assign this box whatever the acceleration is, and it works. See that? And then, of course, if I wanted to go to the moon, let's make this minus 1.6, and it changes instantaneously for us. Okay, so I hope that you're following along. Again, this might not be the most satisfying way to do it. If we were to take maybe 4 or 5 hours tonight, which I not that I wouldn't be willing, it's just my spouse might not like that. All right, so But I've already, if we can schedule another time, I'm happy to take you through anything that maybe didn't make sense here. All right. Now, here's what we're going to do. We're going to build the kinematic equations. All right. I'm going to stop sharing for a second and go back and look. Okay, we're still online. I've learned to check every once in a while. All right. For whatever reason, sometimes, doing last semester anyway, doing classes online, there were times I was on a roll and I realized I hadn't had my students for some time. All right. So I'll just check back every once in a while. Okay, go back to sharing. Everybody's still here. All right, now, what do we need to build this is the kinematic problem solver. I'm going to zoom out just a little bit. Right, so now it doesn't matter where we start this. I'm just going to start at the top. I'm going to call this the time column, position column. And if you're a purist, I suppose you would call it the speed column. I'm going to call it velocity column, all right? This is all going to be in one dimension, by the way. We're going to do the one-dimensional kinematic equations. And as I showed you in that very first slide, this is just evaluating functions. I'm just going to evaluate the kinematic position function and the velocity function and populate them for a set amount of time. That's all we're doing here, right? This is a good exercise to start students on. Not only if you don't mind them using this to solve their problems, or maybe if you want them to do the algebraic version of all those kinematic problems, use this as a check perhaps, or do it both, whatever. It's good for them to use technology, I think. All right. So, but that's all we're doing is evaluating these functions. Now, what we have to do though is populate a time column. All right. And to do this, I'm going to add one more constant that we haven't added yet. So I'm going to go over to column A again, right? And I'm going to call it dt. Right now, certainly, when you do if you do this kind of thing with your students, make sure they understand that we're not doing calculus here. dt is not an infinitesimally small interval, right? And actually, I think you probably could go into Excel or any of these spreadsheets and actually make that an actual uppercase delta. All right, let's not take time and do it. I just always use dt. All right, this is just an increment, and it's what we're going to increment our time column every successive box with. All right, so now we've got to define the name. So in the box adjacent to dt, go up to that name box again, type in dt, hit enter. And now, how far apart do we want our times? We want you can do this, and you can do this separate by a high amount. I'm going to say 0.01. And if we think of time as seconds, then 1/100th of a second. Again, we're just evaluating functions here. It might be good, and I'm not going to do what I would do with my students because of time here tonight, but it might be good to use a relatively large number and just count up to 10 or something like that, and plot with point markers, not lines. Don't connect the dots. Because if the students see something that looks like a function, I guarantee you they're going to think that the spreadsheet is spitting out a continuous function. That's not what we're doing here. We're plotting points. When I make the graph, I'm just going to make it look like a continuous function. I think we can all understand what we're looking at. You would not start this with intro students, by the way. All right. So let's separate it by a certain amount. All right. So here, now go back to the time column. And here's another function of the spreadsheet that is very, very useful. All right. And this corresponds to the concept of iteratively looping through an index, for instance. Right? So I'm going to start time. We always start time at 0. Right? If you wanted to, you could start at something different. All right. Now, here's what I'm going to do. You could imagine if I want to populate every successive row with a succeeding number increased incrementally by 0.1, I could type them all in. But if I want to have, say, 1,000 seconds of time, that's going to be a pain, isn't it? All right. So there's a way to do this, and we're going to use this constant that I defined. So go to the box below the initial time, 0. All right. This is going to equal. Now, this is very important. Choose the previous time. So I'm going to assign this box the time previously at the previous time, right? Remember, I went to increment by dt now. I'm going to let this equal the previous time plus dt. All right? And you can see that it does exactly what I wanted it to. Depending on the value of dt, it incremented it by that amount. Now, you might think, well, what have we accomplished? Not very much. You could have just typed that in, right? But there's this nice little, and maybe you're aware of this. If not, this alone would be worth the price of the webinar tonight. That was sort of a joke. So look what happens. Everybody look closely. There's this little box. And if you see my arrow, if it's Excel, I think it turns from a plus sign to a fat plus sign maybe. But my little arrow turns into a plus sign here. See that? If when it turns into a plus sign, if you do a left click drag, and the reason I say that in words is because I don't remember how to do it on a Mac. All right. So if you're using a Mac, you got to do a left button drag. And that's what I'm doing here. That's what you can see me doing. And I'm just going to drag it down a little bit. And look, there's this smart feature that increments things exactly like we wanted it to do. And it keeps looking one time backward as it does it. All right, everybody see what I did? Now, the nice thing about the spreadsheet, you can double click on any of these, and you can see the formula that was used to actually populate this particular box. LibreOffice is nice. It puts this nice blue box around it for me, but Excel's better because if you're doing this in Excel, you'll not only have the box color-coded with the previous time, but you'll also have DT, the location of the constant DT color-coded in, highlighted. All right? Right? And so you can now just go to the box that you ended on. I'm going to zoom out a little bit. And now you can drag this down as far as you want. I'm not going to go too far. All right, but you could take that down for thousands and thousands of iterations. All right, so we have just iteratively calculated time over and over and over again, something that, of course, you would do in a programming language via a loop. Now, some things like Python and MATLAB, you might do it, you might call it vectorizing it, where you can do that within a vector, but that's just a command that does really the same thing, just iterates things in an array. Right? So this really is a loop, and I like to start students out with loops, by the way. I don't like them going straight to the vectorizing functionality. I want them interacting with the raw stuff as much as possible. Okay, so that was the iterative process. Now, one other thing, look, if I choose any one of these, remember I told you I want the students to be able to make the connection as early on as possible with the real programming language. If I choose, for instance, this box, this is D6, look over on the left-hand side. Hopefully you can see this. Every one of these rows has a number associated with it. That this happens to be the 6th row, it doesn't matter that this is the 6th row. It happens to be the 5th iteration, well, the 4th iteration if we call the initial value the starting point. We've iterated 1, 2. It happens to be the 4th iteration, but it happens also to be the 6th row. And this is where I talk about indexing and using integers to index a location, because this is what you do in arrays in a programming language, right? And just point out, this 6 is meaningless. It's a dummy index. All that means is this is the 6th location in column D. All right, now you can make the same one-to-one correspondence with arrays and array indexes in a programming language. Some programming languages allow you to start counting from 0. Others make you start counting at 1, and it can cause troubles. Right? But it doesn't matter. It doesn't really matter what index you're using. So this is the memory location. It's number 6 in D, and it's assigned this value. So what we've created is an array of values that are associated with my time column. Now, it's not quite the same as a time array, say in MATLAB, for instance, or Python, but the idea is the same. So this is an array, and the students can see it. They can see how many values are associated with this time column or this time array. All right, so this is what I mean by the visual aspect of this. Okay, now let's do this quickly. All right, I'm just going to populate these things, and you can see how I do it, and I'm really not going to talk much. I'm just going to populate this by using the time column, the adjacent time value, to evaluate the kinematic position function at the same time here. So this equals x underscore 0. Now, if you're doing this in Excel or Google Sheets, by the way, it will color code the constant values for you as you do it. Right? LibreOffice is not so nice in that sense. Plus v underscore 0 plus, this is the famous 1/2 AT equation. I'm just going to do 0.5 star Excel star. Now, we want the time. We want the time to change as I go down to successive rows here, because each successive row is a different time. So that means there's no time constant I'm going to point at. I'm going to point to this box here. All right. And that will enable the smart functionality for it to iterate like I want it to. Okay, hit
Should
enter.
the initial velocity have time in it too?
Yes. Yep. We'll do that next.
No, I'm going back to position.
What's that?
Your equation.
Oh, haha. This is where I to get away with this, I would say I was just testing you. Right? And that, by the way, have that one ready for the students, because then you say, I was just testing you. No, I actually made a mistake. I'm glad you caught that. I forgot the V0T, didn't I? So there we go. Was that you, Karen, that corrected me on that one? Or whoever it was. Thank you for.
And doesn't the DT need to be squared for
I was just about to say I was testing you again. All right. Sorry about that.
No worries. I just.
Yeah. No. I was just testing you. I knew I was missing those things.
I didn't know if it was something spiffy that you're going to add to the end that you.
No. That would have been a complete screw up. All right. So I think that's the correct equation now. You're thinking, who is this guy? He doesn't even know the kinematic equations. All right. So that I believe is correct now. All right. So you can see what I was just corrected on. Once again, if you're doing this in Excel, everything's color coded. It's really easy to do sort of debugging as you go. All right. Well, you get that, and that's because we're starting. Let's go back and change the initial position to 0 now. Let's not make it 21. All right. Now you can either drag this down to where you did before, or let's just go to where your arrow turns into a plus sign. If you're adjacent to a row or a column that's already been dragged down to some value, just double click that little box there in the lower right. Do a double click. That's what I just did. And it populates it for you. Or you could drag it down again if you wanted to. Now, by the way, people usually ask, is there a way to populate down to a certain row without having to drag it? And the answer is yes. But I'm going to be hard-pressed to remember what to tell you. I actually always do the dragging thing, even if it's thousands. I just do it. For me, I'm kind of weird. There's something therapeutic about it. All right. So yes, you can probably Google it. You can probably say, how do you iterate many rows without having to drag down? And I'm sure it will pop up, and you'll see how to do it. All right. Very quickly, let's do the velocity here. All right. So this equals, and let's see if I get the velocity equation correct. Plus Excel star. Now I need the time. I'm not going to point to position. I'm going to point to time again, right? Okay. I think everybody agree that that's the actual, it's a linear equation, right? I don't have to square anything. I think I know this equation. Okay. And then you just do the double click or do the drag down again. Right. So now you've got numbers. You've got a column of numbers. You've got a whole bunch of numbers associated with position, a velocity, and a time. These are very similar to arrays you might define. And now what we would like to do is actually plot them. Now this is where what I'm about to do really is going to look quite different in my version compared to if you're using Excel or Google Sheets. And again, I apologize. The thing to do would just look up how to, it just really will look somewhat radically different. Sometimes you can do the following, although I found some spreadsheet programs have a mind of their own. All right, so sometimes if you highlight the columns you would like to plot, sometimes this is sufficient. Now I'm going to do this quickly because this isn't so important of a thing other than just looking at the results. So I'm going to, graphs are called charts in the business world. And I would actually like a scatter chart, and I'm going to connect the dots with lines because it will look a little nicer, not so, I won't have these big fat point markers, all right? And now what I would do with my students, I would take time to, label things nicely and all that, make sure the graphs look good. Okay, and at this point then, we can play with it. All right, so just to demonstrate something real quick, I'm going to make this smaller. All right, so you can all see the graph here. All right, and however you can make graphs. Now, there's several things one can do. Of course, if we want to make the check to see if everything makes sense. If we make this 0, that means nothing's happening. All right, and you just get a line at 0, of course. All right, if we go back to negative 9.8, and now let's give the initial velocity a positive value. So this would be, for instance, calculating tossing a ball upward into the air in the positive direction. And you can see it does indeed reach a maximum height. You can see where it reaches it at, the time at which it reaches, and then it falls down. So this is why I call it the kinematic problem solver, for instance, because any of those one-dimensional problems, even the ones that involve, a race car passes a certain line at a constant speed while another one accelerates, when do they meet? You can program another set of time, position, and velocity for that other car, and you can do all those problems right here on this problem solver, right? So this, remember, plays the role of getting students into the spreadsheet. Just one more little demonstration of why this is called the control panel, by the way, right? We're tossing something into the air at 10 meters per second. Of course, we're not including air resistance yet. But what if we did this on the moon? All right, let's change the acceleration from 9.8 to, say, something like 1.6, about a sixth, right? And look what happens. At least on the moon, for the time that I've allowed, we haven't reached the highest point yet. Now, in order to get to that point, and I do this on purpose with the students, I ask them, why is this only going out to 3 seconds? Remember, the computer's only doing what we told it to. I only told it to go out to however many things I dragged it down to. Right? I only dragged it down a few hundred rows. The increment is 1/100th of a second. And so I tell them, talk with your lab partners, because they're all sitting together, and talk to your lab partners and figure out what we have to do to figure out what the highest height would be on the moon if you tossed it at 10 meters per second upward, and how long it would take. And some realize quickly that, oh, we haven't dragged it down far enough. And if that's the case, then you go back to make an analogy with a computer programming language. You say, well, in that case, you haven't extended your loop far enough, right? You don't have enough positions in your array. You might have to increase the total number of positions in the array. You might have to change your increment and all that sort of thing, right? So I'm going to stop sharing. Okay, that is a demonstration of what I call the control panel. All right, and I'm going to suggest about a 2 to 3 minute break. How about? All right, and then let's come back, and then I'm going to build another model with you in a spreadsheet. Maybe we'll build a few questions or a little discussion, and then let's go right into building another model where we actually use the Euler method to solve a differential equation with a spreadsheet. Okay, I just wanted to demonstrate the control panel and utility of that and the iterative processes in a spreadsheet before we actually do something a little fancier, because I'm going to go fast again. All right, I will be back in 2 or 3 minutes. Take 5. All right, I shall return. All right, everybody. Welcome back. We should have some kind of theme song come in or something. I'll work on that for next time, all right? Let's wait a few minutes. I think I told everybody to take 5, so.
Kelly, this is Bujo Bhattacharya
Yeah,
here.
Pujo, how you doing?
Good. How are you?
I'm fine, thanks.
So
Well,
I
it
had
can
a
be
quick question.
expected. Yeah.
Right, in the middle of a pandemic, right?
Hmm.
Yeah, so I had a quick question. So you of course have you're doing this in a lab with
Mhm.
students, right? I don't have that luxury to do it in a lab. I would like to use these things in my theory class, and I think there is a good place to do that as well in theory
Uh-huh.
classes. The issue sometimes is that students complain that, well, I'm not evaluating them or giving them grades on these kind of activities.
Mhm.
These are just ancillary activities that they want to get points for doing
Right,
things.
right.
So do you have an idea of how you would do that, give them points for doing these kind of activities?
Yeah, so, and I do this even in my non-lab class now. Again, it's a little different format because it's a sophomore junior level, but and I did this though with the interest students too. Um, I have them write it up. Just describe what they've solved, and they have to include. There's certain things I make them include in their spreadsheet. In a spreadsheet, it's possible to put in name boxes, for instance, insert name boxes, and that's sort of like commenting your code. All right. So I actually do evaluate it. I have them address certain aspects. I create exercises that they're going to use their model or their simulation, whatever it is, to address. And it's not quite a formal, full-blown lab report, but I call it a memo format, for instance. And I just, you can't start too early in learning how to communicate written results, whether it's, a lab or whether it's computational stuff, whatever. So I actually do try to evaluate everything they do.
Thank you.
Yeah, I mean that you almost have to do that. Otherwise, now some of my fellow pickuppers, Marie Lopez del Puerto from University of St. Thomas in particular, she actually puts this stuff on exams. Now she has extended exams. She does it during lab times. And so again, there's some, institutional based luxuries involved. But she actually puts these things on exams and tells them this stuff's going to be on a test. You're going to be tested over it. All right. So it is possible to do that, Buja. I mean, we can talk more about how practical ways to do that. You know what we should do? Maybe later in the semester, we'll do a webinar on evaluating computation, assessing. I guess. I mean, I don't
Yeah, that makes sense to
necessarily
me.
mean. What's that?
That makes sense to me, to talk about
Yeah.
evaluations.
Yeah.
And like as you were saying, like there's also institutional luxuries that some people may have, which some others may not have, right? So
and sometimes there's good workarounds. I know people have found ways to work around big classes. All right. So there are ways, and I think I'll make a note, and we should maybe have some webinars this fall on these kinds of things. Okay?
I mean, I have used these in like team-based activities where I have a section of my course which is I call it team projects, and I have them do these kind of some sort of computational activities. But I'm not very happy with the quality when I'm giving them points. I'm not very happy with the quality of it, of the work that I get. So
we can. Let's try to do a webinar on this very topic. That way we can continue this. Although again, I've already offered, but I'm happy to meet with any of you to the extent you think I have something to tell you. All right. So let's continue, and I want to build the next thing now. looking back, let's see. Oh, hold on. Let me share again. I always forget to share my screen here. All right. So now you should see. All right. Can someone unmute and say yes or no to looking at the slides again?
Yep.
Okay, got it. So again, this is really the very ambitious approach to my curricular change in the intro mechanics course. I'm going to take you through the falling sphere now. All right. Before we do that, just oops, I didn't mean to do that. A very quick refresher on the Euler method. And I don't mean to insult anybody's intelligence, but just to show you, because I want to demonstrate in this model we build, I want to demonstrate how you visualize the building of an algorithm, all right? And that's what I want to do. By the way, please keep in mind, what I'm showing you is not the starting point with my students, all right? I spend quite a bit of time talking and giving them activities where they are engaged and interact with the concept of an approximation. In particular, approximating a curve with a straight line. And I put it to them, and we do cute little things, and I have them think about it and discuss it. So I don't just pop the slide I'm about to show you in front of them, although we do get to it at some point, all right? So here's the Euler method. The as seen on TV version is this function here, all right? You see the little wiggly equal sign in this equation. That means left-hand side, the velocity at some generic time plus some increment, delta t, is approximately equal to the velocity at the generic time plus the acceleration at that generic time times the increment itself, right? Now, this is utter nonsense unless it's an approximation, and even then, we have to decide under what conditions this is a good approximation and that we're able to get away with it. All right, so let me just show you, and I'm going to fly through this slide quickly. I've got a bunch of slides like this. If anybody's really interested, I can share these with you and what I do with the students. But for the sake of building the model that I want to get to, let's fly through this. So let's say we know the velocity. This, by the way, this is a velocity versus time curve. I don't know what it is. It's some changing velocity with time, and obviously it's a changing acceleration with time. This could be a rocket, for instance, something, right? But it is something that we actually don't know the velocity at later time. So we know the velocity at time t, right? That's the starting point. But we, for instance, don't know, for whatever reason, we either don't know the function or it's an experimental observation, and we're going to have to try to approximate or figure out what's happening out here at a later time, right? Right. The simplest way to figure this out, I say this is our goal. We want to know the exact. Of course, if we knew the exact, we wouldn't be approximating anything, right? But that's our goal, is to try to come up with the exact or as close as possible, right? So there's this line. Look at that red line. Everybody see that red line that just popped in, right? I call that the Euler line because the simple Euler method is, all that is an attempt over that time interval from t to t plus delta t. That's an attempt to match that curve with a straight line. Right, that's all the Euler method is, right? Every student should know, right, that the derivative of the velocity is acceleration. And so if I draw that red line tangent to the curve at time t, that represents the instantaneous value of the derivative at time t, or the instantaneous value of the acceleration at that time t. And then if you extrapolate it out here just linearly, then where that crosses the time t plus delta t, that becomes the approximate value of v at the later time. Now you can see we failed miserably by using the straight line, right? Certainly for the scale shown here, that straight line does not match that curve, does it? But look, if now if you go back and say, well, let's make the delta t smaller, and look, you see the discrepancy here. The discrepancy, what I mean by discrepancy, the difference between the exact value at t plus delta t and the approximate value is our error, correct? And that, as we make delta t smaller, in other words, move delta t closer to the original time, and you can see the discrepancy goes down and down and down to the point where, at least on this scale, it almost disappears. In other words, that black line and the red line are almost inseparable. You can't on this scale see it. Of course, you can always zoom in and see that it's different. It only becomes exact once delta t goes to 0, but then we're back to calculus, all right? So for whatever reason, we have to use calculus to solve this thing. So we could spend a lot more time. That's the simple Euler method, and it is embodied in this simple equation here. Okay, but that only works, and I just tried to demonstrate that graphically to you. This only works if delta t is really, really, really small. How small? Now that depends on a lot of things, and I found the best way to determine just how small is to have the students actually investigate this on their own. All right. I'm outside. I hope you don't hear that pounding, and I hope that it doesn't become too annoying. All right. I can't imagine this time of night is the perfect time for my neighbor to launch into a project, but you never know. All right. So now I've got a few other slides. Let's not take time with this. All right. But I can share these with you. This just demonstrates that we're actually accumulating local error, and we're not just accumulating error from the exact value. We actually accumulate it from the approximated value of the last time step. And so as you go to what's called global error over many time steps, this can get really big unless delta t is small. The message to take away is, in the Euler method, you got to keep delta t really small. All right, so let's not spend too much time with that. But here's what we're going to model. All right, and I'm going to populate this quick. Again, you can look back. Trust me that the physics is correct. If we have something, a sphere dropped from the Sears Tower, it will experience gravity and a resistive force. This is the form of the resistive force, where these are the parts of the coefficient in front of the v squared term. All right. All right. We're going to start with 0.5. I can tell you why we're starting there in a moment. But this is the form of the drag force that's used in wind tunnel experiments, for instance. And the way that the engineers deal with the drag force changing with velocity is to let d itself be a velocity dependent thing. Well, we're going to start out pretending it's a constant. All right. And actually, that's a good approximation over a certain range of Reynolds number, but don't worry about that. That's a fluids thing. We can talk about that later, right? So applying Newton's second law, you come up with this. And finally, if you do, whoops, where's my exact, let me stop that and actually show it, not in slide mode. I don't know why it didn't show up in slide mode, but I think you can see it here. This is the acceleration function as a function of time in terms of all of these parameters: drag coefficient, air density. A is the cross-sectional area, or what the engineers call the frontal area sometimes, and the mass. All right, and there's our good old friend G. So in our model we're going to implement this in a spreadsheet, and we're going to see how this behaves. Okay, so that's the plan. And you'll notice that there is no explicit time dependence. All right, the acceleration depends on time because we have a changing velocity. So it's due to this inherent changing velocity, all right? Okay, so that's what we're going to build. And so if you haven't already, fire up a blank spreadsheet. And if you want to try to do this as I do it, I'm really going to go quickly, though. I have to warn you. So it might be best to watch maybe what I'm doing and try to do this on your own later and use the recording as a cheat. All right, that's one way to do it. So what I'm going to start out with, we need a delta t. That's one thing that we're definitely going to need. All right. And we're also going to need, so that's going to play the role of the real delta t. Now remember, I don't want to confuse anybody. This is not an infinitesimally small interval. This is actually a real delta t. Okay. We're going to solve a differential equation through that Euler approximation, and we're going to try to make this small eventually. All right. So we also need starting points for the position. Let's call it y. It doesn't really matter what we call it, since it's vertical. And you can actually build the model. It doesn't have to be the Sears Tower. It could be anything as long as you let it fall far enough. You'll notice my spreadsheet is just aching to make that a capital Y. I don't know why it does that. We need a V0. So what I'm doing in column A, I'm putting all the names of the parameters in, or the names of the names. That's what the spreadsheet calls it. These are going to be all the constant parameters that we're going to use in that calculation. And then we will use the values of the various columns to build our model. All right. So, so if you need to look back, you can, although you can also trust me. Now, what I like to do, and I tell the students this, I like to use names for the variables that are meaningful. You could use D and A, but I like to put a few letters to it, all right? It's just good practice to get into. So I'm going to call our good old friend acceleration due to gravity, grav. Right? The air density is rho. Okay? We need the mass of our sphere that we're going to drop. You'll also notice, look at this. If you look back here, A shows up. That's the area that's presented by the falling object in the direction it's falling. And it makes perfect sense that the drag force should be proportional to this area. So if it's a sphere, of course, then the area presented in the direction is a circular area. So we need to know, if we use pi r squared for the area, we need to know the radius of the ball. So I'm going to do this. I'm actually going to include radius, RAD for radius, and then we'll calculate the area based on the radius. The reason I'm putting the radius in instead of just directly calculating the area, it makes it easy to switch balls. In other words, I can build this model for a basketball, let's say, and then all I have to do is change the mass and the radius to simulate a baseball. Again, that's why it's called a control panel. You can just change things instantaneously and end up modeling a lot of different things. All right. Finally, is that everything? We need a drag coefficient. Remember, I'm going to call it drag. All right. That's that magical D that shows up here. A little bit more on that later. All right. Okay. So I believe those are all the parameters we're going to need. And as I already demonstrated for you how to build the control panel, that's what I'm going to do. I'm going to do it very quickly. And so I'm not even really going to talk much while I do it, and then we'll populate it with numbers in a moment. Okay. So let's do it here. I'm going to do it with the name box approach. The Y is position. I'm labeling, I'm defining names, the exact same thing that shows up over here, so we're not confused about what we're building into the model. Add for radius, don't forget. Yeah, you might want to spell out radius completely. I'm taking a few shortcuts tonight just for the sake of time. One thing I would do, by the way, if I were doing this with the students, I would have a third column which actually labels exactly what these are and says what the units are. And in a computer program, I would have them do that also as a comment. All right. Okay, so I think I've defined everything. Let's put some numbers in, and we can change these later. I'm just going to populate them with numbers. So I don't know. I'm going to start out with 0.1, a tenth of a second. I don't know if that's going to be accurate. Actually, let's make it 1. It doesn't matter what we make it. I don't know if that's accurate or not for a solution for the Euler method. We're going to have to investigate that and check it, and I'll show you how to do that. Let's drop it. Now, notice one other thing. Let me point back to this, and I get criticized for this all the time. You'll notice I've called the down direction positive so that when you apply Newton's second law, it's mg minus the drag force. That doesn't matter. You can call down negative if you want. I just do this because I do it on purpose a little bit, because I tell the students you can define plus and minus however you want. Your books always do it negative is down. So don't yell at me too much for doing that. Just don't be confused. So let's call, and since the down is the positive direction, if we start at 0, if it's the Sears, by the way, don't correct me on the Sears Tower. I know it's now called the Willis Tower. It's always going to be Sears Tower in my heart. All right. Don't correct the teacher. Okay. So if we start at the observation deck, the pavement is about 440 meters below that. So plus 440 meters in position is the pavement. All right, just be aware. Let's drop it from the Sears Tower. So we'll start at velocity 0. You don't necessarily have to you could hardwire these in the columns, but I like to start this because then you can change them. You could throw it down, for instance. All right, here is our good old friend. We'll take care of the direction and the negative sign's already taken care of in our expression. Close to the Earth's standard pressure is something like 1.29 kilograms per cubic meter for rho. That's about the air density. Now, let's drop a basketball. All right. And I don't know how I know this. I've done this enough times. I've got these memorized. An NBA regulation basketball is about 0.625 kilograms. Right. And I happen to know the radius too. I'm rounding it up, but I think it's something like 0.12 meters. Yep, it's about 0.12 meters, if I remember right. Okay, now I'm going to calculate the area directly from the radius. Once again, I'm doing this on purpose because now if I want to use a different ball, all I need to know is the mass and the radius of the thing, and I can change this to simulate something else falling. Okay, so this is going to be equal to, so remember we're assigning this. Pi is built into the spreadsheet, by the way. If you have empty parentheses, that knows the number, our good old friend pi. Pi times RAD raised to the second power. And that is the area of the basketball presented in its direction, the circular area in the direction of its motion. And remember I said we're going to start with a value for the drag coefficient of about 0.5. There's a good fluid dynamics reason for that. I can share it with you later, right? So, and that's a pretty good approximation to start with. All right, so I think that's everything we need. Okay, and now we build our column. What do we need to model this? We need a time. It's pretty much the same thing we needed before. Velocity, but let's throw in the acceleration column, just because it's not constant like it was in the kinematic equations. And so I like to. Now, if you wanted to, you could add other columns. You could make a column solely for the drag force and watch how that increases with speed, for instance. So you can get at everything here. And these computational exercises, you can do about anything. It's so much more, the students are able to take ownership so much more readily than they would with algebra problem, doing those analytical problems alone. Okay. Okay, so let's start with time. So now, everybody think with me. We're not evaluating functions now. We're building an approximation to a differential equation. That means every successive time now is going to be another discrete solution to the differential equation. Okay, but it looks the same. We're going to increment time with some value. It's just eventually this time increment's going to change on us. All right, because we're going to investigate the accuracy of the solution. All right, and I'll show you, once again, I'll show you how we're going to do that. All right, so let's build this now. All right, let's start at time 0. At time 0, standing on the observation deck, we're holding the ball at position 0. The pavement's plus 44 meters down, and I'm going to drop it at 0 initial velocity. Okay, so the next time is one time step later. All right, one time increment later. So we want this, and again, we're assigning it. So remember how to do this, how to take advantage of this smart iterative functionality in the spreadsheet. You let it equal the previous time. So the time, one time step later equals the previous time plus the incremental value or the time step value, dt. Hit enter, and it did what we wanted it to do because we're at 1. Right now, we go to what I just programmed. Right? And we're going to iterate it by dragging it down, thereby populating our time array. Time column in a spreadsheet, but it plays the same role as a time array. All right. So I'm going to drag this down a lot. Actually, not so much here. This is where, if you're going to systematically observe your solutions for smaller and smaller delta t, this is where you want to drag it out to thousands. And it doesn't take that long to drag it down thousands. You see, I already got to 1,500. I would drag it down quite a bit more, up to maybe 10 to 20,000 rows. And my little laptop can handle it. And your little laptop can handle it too. That's an array of 20,000 values is nothing for the memory we have in our machines. All right. Now, let me stop sharing real quick just to take a peek. Okay, everybody's still here. Looks like I'm still going, right? Okay, good. Okay, back to sharing now. Trust me, I have to do that every once in a while. Okay, let's share again. Okay, and back to our spreadsheet. And oops, I said back to our spreadsheet. Can someone unmute and say, I see it? Can you see the spreadsheet?
I see it.
Thank you. Man, I was worried there for a moment. All right. All right. So now we've populated the time array. Let's do position. Now, actually, let's not do position. Let's do the initial position and velocity. And it doesn't matter what order you do it in. I just like doing it this way. Over the years, it's the least confusing approach, I think. So let's put the initial position in. And remember, that's over here. So I do x underscore 0. Oops, what happened there? Oh, y, right? There's another one where I say, I did that on purpose to see if anybody's paying attention. Y0, I called it y underscore, not 0, not y x underscore 0. Okay, now, of course, we could change this, and it would change the position. So that's set, but let's not program the position or the velocity. Remember, we're not evaluating a function here. We're going to build an algorithm based on simple Euler method. Before we do that, let's put the initial velocity in. I'm assigning this first. Oops, the initial velocity, I'm assigning it to be v underscore 0. Once again, if you're using Excel, it lights it up over here for you. It's very easy to follow and very easy to sort of debug on the fly. All right. Okay, now, before we build the Euler algorithm into these two columns, because that's what we're doing, we're going to use the Euler approach to approximate velocity based on the previous acceleration. Then we're going to do the same thing for position based on the previous velocity. And as I've promised, this is a very visual way to build algorithms. And after you do this a few times, you fall in love with it. And you can recognize just by looking at a student's columns if they got the algorithm right. All right, just by, I'll show you what I mean by that. Okay, so let's program the acceleration. Now remember, the acceleration is a function that Newton's second law spit out. This is exact. We're not going to be approximating the acceleration, although the values that go in subsequent times will be approximations themselves. All right, but at the beginning, it's just it's a function we know, and we program it in. Right, so it equals this. Now be careful. If you thought I had trouble with that horrid kinematic equation, watch this. All right, so I've done this enough times, I don't think I have to look back, but hopefully I get it right. So the first term, if we do take a peek back, the first term is gravity, g, minus then this whole thing here. All right, I'm just going to type it out, and then if we need to, we'll look back and make sure I've got it right. Minus, so drag times rho times that frontal area. Everybody see? Now, I'm going to run out of room here, and you're going to see that it's going to wrap around down to the lower level. Right? Don't be afraid of that. You should actually see this to see what it looks like. Times. Now, here's what I'm going to do. Remember, the coefficient is times. We're assuming that the drag force is proportional to velocity squared, instantaneous velocity squared. And that's really the next term. So what I think I'll do is I'll put that in, and then I'll divide everything that's multiplied there by the quantity 2 times mass. All right. That way we avoid a whole bunch of parentheses. And that's one thing, if you do this with your students, students are just aching to use parentheses. They want to put parentheses around everything, and it makes it almost impossible to read and look at. So from the start, I try to urge the students, don't use parentheses if you don't have to. Understand the mathematical hierarchy of multiplication and addition and all that, right? So this is what it looks like. Now remember, it's v squared. There is no v parameter. I've got to point to the velocity column because we want to use velocity at each successive time step to populate or evaluate the acceleration function, right? So I'm going to just choose the velocity at the same time step. Don't forget to square it, or you could just multiply it by that again. Doesn't matter. This works just fine in the spreadsheet. Okay, but now remember, that whole thing's going to be divided by the quantity 2 times mass. If you don't believe it, look back. 2m is in the denominator there. All right, so let's go back and divided by quantity 2 star mass. Oops. And you can see where it wrapped around down below. All right. And I like to stare at it and think about it. Is it going to do what I really think it's going to do? And you know that it will do this parentheses first, and then it will raise this to the power, and then it will start with drag and go right down the line. And that does exactly what I want it to do, I believe, right? Okay, now look, we get 9.8, and I try to tell the students, because remember, I've said that I believe this is a good level for them to interact with the computer, all right? If you go straight to a programming language, especially an interpreter like Python or MATLAB, and then you try to plot it right away, plot what they come up with, they never look at these numbers. Now, you can make them look at the numbers, of course, but here you don't have any choice. You can see what the computer is doing for us. It's just calculating things based on what I told it to calculate. So if this number isn't correct, it's because I made a mistake, right? Now, look, you get the acceleration due to gravity out because the velocity is 0, and then you should really point back and say, that's what it better be. We're not moving yet. There's no drag force because we're not moving yet, all right? Okay, now that acceleration is programmed for all times now. And all I have to do is drag that down. I'm only going to drag it down a little bit, and that'll be obvious why in a moment. But look, we get 9.8 for all of these values because it's looking, remember, and you can click on any of these. Click on any of these to see the formula or to see the equation that was assigned. And it's looking at all the constant parameters. Again, if it's Excel, these will be lit up, nicely color-coded. But it's also looking at F4, this box here. So it's always looking at the velocity at the same time step. But I don't have anything in there yet because I haven't built the model, the Euler model, and so it thinks it's 0 on all these. These acceleration values will get updated properly once these are all populated over here. All right, so that's done. Now it's time to solve the differential equation. All right, looking back, remember, we're going to do simple Euler. And let me go back one just to remind you what it looks like up here. All right, here's the Euler equation, and we're going to do exactly what this says. And I tell the students, look at this form. This is a very useful notation, this functional notation with the parentheses. I tell the students, do in your spreadsheet exactly what this tells you to do. The list says the value of the velocity at one time step later than some t is approximately equal to the value at the previous time plus the value of the acceleration evaluated at the previous time. Previous meaning the generic t, later time meaning the t plus delta t, right? And then you multiply that a of t times delta t here. So let's remember that. It's and again, what's got us to this point with you, hopefully you, certainly with the students, we spend a lot of time thinking about the nature of approximations so they know this and it's dear to their hearts, all right? So let's put it in. So look, here's how you build it. This is the next velocity. This is the velocity we're going to program. It's one time step later than the initial velocity. So this will be assigned. And let's do what Euler says to do. It says use this is equal to the previous velocity plus the acceleration at the previous time step. Well, we've got it right here. It's right in front of us. It's that one. See that? Times the value of the time increment itself, or the time step itself, right? Okay, now, once again, I like Excel much better than this version because if you're watching me online, it's not color-coded. Although I think if I hit enter and then if I go back and double-click, it does indeed color-code it for me. I don't know why it doesn't do it as I do it. In Excel, everything gets color-coded, and you can see if you're doing it right. But look, you can see this blue and red boxes. I have built the algorithm by choosing the velocity and the acceleration at the previous time step. That is the simple Euler method. And you can see it has populated now the proper value of the acceleration because the acceleration is using this value. And it has started to go down as one might expect it should do if the drag force is present as it starts to fall. The acceleration should start to decrease. So everything is right with the world so far, and you should ask your students, Did this number make sense? Because if it doesn't, then that means already we're not on the right track with solving this thing. We don't yet know if this value is accurate yet. Keep that in mind, right? I don't yet know if this is a sufficiently small delta t to make this value at the first time step accurate, but we're going to investigate that, right? Is everybody with me? Okay, once again, I double click what we just did, and that's the Euler method. We're going to do the same thing over here, but instead of acceleration, remember, velocity is the derivative of position with respect to time, as acceleration is the derivative of velocity with respect to time. So we can do Euler here to integrate this thing. We just use the previous position and the previous velocity in the Euler algorithm. Now look what happens here. All right, let's program this. And then what we'll do once we get the position programmed at the first time step, we'll highlight everything and we'll drag everything down together. It will iterate multiple columns just as easily as it does single columns. All right. But let's focus on the Euler algorithm here. This equals the position at the previous time step plus the velocity at the previous time step times delta t. Now, you can see already what's going to happen. Everybody see what's going to happen? Since we're starting at the initial position, or sorry, initial velocity, we're starting at 0, we're dropping it. That means I'm going to get, for the first updated position, I'm going to get a big goose egg. Look at that. See that? Now remember, when you're doing this, you have to have your students paranoid. They've got to be paranoid about these computational solutions. They should be paranoid about analytical solutions, although we don't teach them to be, but they should be, and they should definitely be paranoid about what a computer's telling them. All right? And as I just spent time, a little bit with you in class, I really dwell on this, pointing out that this number that shows up anywhere better make some sense. The acceleration went down, the velocity increased. Look what happened. It didn't go anywhere in position. And I asked the students why, and it really is very entertaining to me. I shouldn't share this with you, to see the students get bummed out about this. They try to figure it out, and they try to figure out what went wrong. There's nothing wrong. This is the nature of the approximation, and it's the very first point. It's the very first opportunity that you get to spend with the students in pointing out that this is not an exact approximation. There's a flaw here. This is artificial behavior, all right? But you can also bring to bear that we can rectify it if we made delta t really small. And so let's say we made it, and let's not do it right now, but let's say we made this a millionth of a second. Then I think even the students would agree, well, if it doesn't increase for a millionth of a second, that's not a very serious artifact, is it? No, we can kind of live with that as long as it doesn't affect the next time step. Okay, and as we're about to see, it doesn't indeed affect the next time step. So look, this very first artifact that we tangibly interact with in a spreadsheet, you would not see this in a programming language if you had your students do it. Even if you gave your students a partially working program and said, here, add the acceleration or add the Euler method for the position, they would probably very likely not interact and therefore miss a golden opportunity to bring to bear the concept that what you're doing is artificial here. And it's only going to become accurate if we play around with this delta t, all right? So let's do what I said. We can get rid of these numbers here, or we could keep them. What I'm going to do is highlight all three of the things in the first time step that we just programmed. That means all three of these. Since all three of these columns are adjacent to one that's been dragged down, you could either grab it and do a drag, or you could hover and do a double click, and it populates everything for me. All right. Okay, so everybody see that? Now let's just click at a few places just to show you that this algorithm, this Euler algorithm, has indeed been preserved. The first thing I want to point out, look, the second time step in position has indeed been populated with a number because, once again,
We lost you.
Yeah, you're gone. I think he froze.
It's a great facial expression.
Yes, indeed.
is all we
How's everyone else doing?
I'm having fun, I think.
Yeah, I'm learning. I never done the Euler method on Excel before, so
Yeah, we're hanging in here. We're watching to see if our students behave. We've been back in school for 2 weeks now, so this is the week that we find out.
Right.
yeah, this is my 3rd week back. So I'm trying to get ideas for labs this semester. And always going back and forth between the argument of spreadsheet or MATLAB or Go Python. I always go back and forth in my mind.
We're running 36 sections of online labs for the first time. Lots of fun.
Ooh.
800 students.
Whew. Where are you at?
North Carolina A&T.
Oh, I thought so. I thought you looked familiar. Okay. I'm at Durham Tech Community College.
Hello over there.
Hello. I went to a physics conference there a year ago. I think you guys hosted.
Right.
And you also hosted Engineering Pathways, which I'm also active in. I'm actually sending a student your way. I'm really hoping she minors in physics or possibly double majors, but we will see if she does.
Okay.
So I was really impressed with her in my class, and she's at A&T, and she says she's interested in taking Physics 3. So I'm hoping.
Okay.
It looks like, given the outline of the labs, that at the end of the semester, he's expecting students to be able to apply. I mean, just to execute with spreadsheet and to understand and implement Euler's equations. So, solution of ordinary differential equations as a course objective.
I think for my Physics 2 class, I can play
Hey
around.
everybody. Are you am I coming through?
Yep.
Now you
Yeah.
are.
Oh, looks like you froze again.
Yeah, it looks like he's
Yeah.
frozen again.
So how does the link stay up if he's gone?
They usually make somebody else be the moderator. So who's the moderator?
Ooh.
It does an automatic. At least other apps do it. I know my the 2 apps like.
Hey everybody. Am I coming through again?
He totally
Yes.
changed.
Now.
All right. I apologize. I'm glad I warned you all. This has happened before. I hope you had a nice break. And by the way, it's getting dark. I don't know if you can see me. I'm still outside,
I noticed that.
and it still is the most peaceful place in my household. All right. So, what did you last see? Can somebody tell me what you last saw?
You were on the spreadsheet. You were going down to fill the cells, and then you froze. The cells populated. Acceleration went to 0. Velocity was terminal. Then you froze.
I think he's frozen again.
Which you froze again.
And you.
I don't know. Perhaps his Wi-Fi is a bit unreliable outside.
Oh my goodness.
Or maybe his neighbor did something with that chopping that they were.
There.
Okay.
Well,
Try
She's coming.
again. Am I coming through to anybody?
Yes,
Yeah.
you are.
I apologize. I don't know why this is unstable. Okay, it seems we're back, hopefully. Can you give me a hint of where I was when we disappeared?
When you were iterating the solutions and the acceleration went to 0, and then velocity stayed at negative 20.5.
Okay.
20.4, yeah.
Okay.
And so we didn't even talk about that. You just iterated.
Oh.
And then
Okay.
you froze.
Okay. So you saw the position stay at 0. Is that correct?
No, we got past the position is 0, but we iterated all the way down.
Oh, okay. So you saw the Euler algorithm.
Yes.
Okay, good. Well, then you didn't miss much. What I would like to show you, and hopefully you can stay with me. All right, let me share again. So what I'm going to do is now, instead of taking the one we just built and then building from there, I'm going to show you the finished the finished product next, and show you what we have to do in order to investigate the accuracy. Okay, and so hopefully we stay together now. And actually, hold on. Okay, and let me share the screen again. Okay, hopefully I am sharing, and you can see now a slide. Can someone say, yes, I see it?
Yes.
All right, good. Okay, so in order to investigate the accuracy, I start out with, and this is the luxury of the falling sphere. If you integrate this, and you can still integrate this, by the way. I don't have the students do it. They're already afraid of the drag force proportional to V alone. Even reminding them that they've probably done something like this in their Calc 2 class doesn't assuage their fears. So I just show them that you can integrate this as long as D is constant. You can still get an exact solution, not only in velocity, but you can integrate it again. Now you end up with these horrid functions. All right, but that's what you get. And so I like to start out with this falling sphere, and I compare the Euler method, the Euler solution, to these exact solutions and demonstrate how to approach accuracy. All right. And let's go to the one. Oh, I got to open it. Just a second. And let's see here. And here. And here. Oops, that's not it. Here. And here. All right. Okay, now can somebody unmute and say that you see a falling sphere finished version?
Yep.
It looks like we're all still together. Don't worry about that. I just had to check. All right, good. Now look, everybody. So this is the exact same thing we just built. The control panel looks a little more complete. It's color coded. Right. I've got all these positions. You'll notice I've added to the velocity, position, acceleration. I've added V exact and Y exact. And I have them plotted here. All right, so the red plot is the exact based on that integral I just showed, based on integrating this hyperbolic tangent function. All right, and oops, back to the spreadsheet. And the blue one is the Euler solution. Now I think I don't remember if I showed this on the webinar. It doesn't matter. Let's take a little more time and investigate this. And you can see, and this is what I emphasize with the students, making really nice looking graphs. That's a skill they have to know how to do. They have to have it labeled, obvious what we're looking at. And actually, I'm doing this a little different than I would do with them for the first time. I would have them use points here. I wouldn't be connecting the dots because we really want to emphasize we're only getting solutions at discrete points. And all we're doing at the red line here even is evaluating the exact solution at discrete points and making a comparison. But as the points get closer together via a systematic lowering of delta t, then it starts to look like a continuous function. Eventually that happens even with point protectors. And so, but for our purposes here, I think you understand that we're not generating a continuous function, of course, right? So this is another thing, and you have to do this with the students. This is this paranoia I've already talked about. So if I lower this, for instance, from 3 to 1, the red solution, of course, stays put because that's the exact solution you get from integral calculus. The blue one starts to approach it, though. See that? Let's go back to 3. Everybody see this? All right, good. We're still connected. All right, and so I tell the students we have to decide how small delta t is before we can deem that this is an accurate solution. And what better way to start learning this skill of evaluating the accuracy of a computational solution than to compare the computational solution with an exact one? Okay, now I know what you're all thinking. You're all thinking, well, but in the real world, you might not have, and most likely you don't have an exact solution to compare to. But keep in mind, even if the red one was not here, we would be observing the blue curve approaching and converging towards this red one anyway. That really is the key to look for in any of these computational solutions to these differential equations generated by Newton's second law. Any physical model you can build like this, you look for the convergence of the solution. That's how you know you're approaching accuracy. And there's many ways that you can tell the students to look for this. For instance, taking 2 points and calculating the difference between the two, or physically, visually observing it like this. There's many ways they can do this and do it accurately. All right. So let's systematic. I'm just going to sort of take you through the systematic lowering of delta t, and you can watch what happens. Delta t is 1. Everybody see that? Okay, it's 1. Let's go to 0.8. From 1 to 0.8 seconds. Better yet, right? It didn't move too much. Let's go from 0.8 to 0.5. Everybody see that? Let's go back to 0.8. Not as good. Better. And the students can appreciate this. They can visually see that they're controlling all the calculations that the computer's doing for them, and they're investigating the accuracy. Now, at some point, let's say we get down to 0.1. Oh, let's do 0.25 next. From 0.5 to 0.25. If you look really closely, I can still see a little red and blue. Interestingly, by the way, the lower time solutions and the higher time solutions are pretty close, but there's this middle section that isn't working too well. By the way, if we go down and look at the position versus time, it's not as good. The velocity solutions are a little more accurate than the position versus time, and that might make sense because we're one more derivative or one more Euler method removed, right? Should all make sense, okay? But the point is, as we make delta t smaller and smaller, we approach so if I get down to 0.1, suddenly you can't distinguish between these. And so all the students, there's almost a collective whoop goes up that, we've arrived. And therefore, delta t equals 0.1 must be the magical number that solves this differential equation. Okay. I just got told I was way too loud. Sorry. Can you still hear me? If I apologize. I get excited about this stuff, and so I get worked up and I get to talking loud. I think you may have noticed that. All right. Can you still hear me if I talk like this?
Yes.
Okay. Man, I must have been blowing you all away. They're complaining on the second floor with the window closed. All right. So back to this, and we're almost done, really. Of course, you can zoom in here, right? And I don't know if it's going to be worthwhile to take time to zoom in. I would just maybe zoom in between time 6 and 8 here and velocity 50 and 60, and you'll once again see that these solutions are separated by a gap, right? And oops, I didn't mean to do that. And of course, you can keep lowering delta t. And so the message becomes to the students, it's not just an absolute value of delta t, it really has to do with the particular problem we're solving and the error tolerance we have for the solution. Now, if we're talking about dropping a ball and modeling a ball that's falling from the Sears Tower, even if we went across the street and filmed this event, wouldn't that be cool to do the experiment? Even if we filmed this event from across the street, probably our error in pinpointing the position of the ball wouldn't be I doubt if we could get 1/10 of a meter, right? Something like maybe better, but maybe not. And so already in our solution, we have much more accuracy than we could ever compare experimentally, right? But who knows? There's other things that one could model and simulate. Let's say you're a biomedical engineer and you're working on designing a new, medical instrument, and there maybe the accuracy someone's life may depend on how well you model it and design it. Then we better have more accuracy, right? So the answer is, how accurate do you need to make these? The answer is it depends, and the students have to grapple with this. And so, I think let me stop sharing here. I think I showed you the list of things that I do with these students. And when we get to the next one, which is usually modeling the orbit of the moon around the Earth, there you have a different time scale. And there the students are blown away because of the different time scale, and a different value of delta T completely produces different behavior. And so that really hammers home this idea that accuracy is a system-dependent thing that they have to learn to investigate. Right? And even then, you can point out that you will never, hardly in real life, have an exact solution to compare to. And so what we really have done with that delta T lowering exercise is force the convergence of the solution. Right? And that's really the thing to look for. The comparison isn't even that important. All right? So, Mark, for instance, I know you asked a little earlier about the accuracy of the Euler method, and I think I've tried to demonstrate that you can get away with it. Depends on the situation, the solution. If we did have time, and if we did go through, and I can provide you all these things, by the way. If we did do the orbital problem now, and we built that, you would see that there's another issue comes into play, that the simple Euler method simply does not conserve energy. And this is where it allows us then with the students to bring up the concept of a symplectic algorithm, which is a very fancy way of saying something has to be conserved. And we make one small little minor adjustment to the Euler method. It's called the Euler-Kromer method. In updating the position, we use the velocity at the later time, not the earlier time, to actually update the position. And that's enough to conserve energy. So, Mark, Euler gets us pretty darn far.
I see that.
Yeah. And you can do it in a spreadsheet. Like I said, this is being recorded. I think the recording's intact. I'm not sure what's going to happen during the gap there when I'm gone. I don't know. Anyway, like I said, I will post this, and I'll post the slides, and I will make available, and I'll show you where it's going to be available, all of these different spreadsheet implementations of these things I have. And you can look at it, and then as you see fit, I'm happy to meet individually, however it might work out. So how about if we call that enough presenting for the night? And maybe before we call it an evening, maybe field some questions or any comments you might have.
So, Kelly, I would love to talk about bridging to MATLAB at some point with you, because I'm trying to bring more computation into my classroom, but I go back and forth between whether to do spreadsheets or MATLAB or Python, but I do think a spreadsheet MATLAB or a spreadsheet Python combo would be best. I'm curious to see the work that you did for moving from spreadsheet to MATLAB throughout the semester and how you built upon those.
Sure.
I mean, at another time, of course, but I was just...
And what class is it, Brittany? I
teach calculus-based physics 1 and 2, but they're all have their eyes set to go and become engineers.
Yeah, sure.
So they want to transfer. Okay.
I have quite a bit of materials that I can share with you. Okay. And again, there's no secret. It's using the spreadsheet, doing what I just did with you all and what you just watched, and having them do that not only with me, but having them do that themselves so that they become adept at the spreadsheet itself. But then when we branch out to, say, the simple harmonic oscillator or the damped driven one, using the spreadsheet as a guide then, because they have it, they've already investigated, as I just demonstrated for you, they've investigated the accuracy, they know what to expect. And so then if their spread or their MATLAB version or Python, whatever it is, if it spits out nonsense, they know it. And they know that something's not right. And they know to go and debug. And it doesn't take long. I mean, it really doesn't take but a few of these before they can tackle something almost from scratch. And I'm not talking everybody, of course, but the vast majority of students can do it at that point. So I've got stuff I can share with you.
So for a lab, as far as time frame, how long do you let them have on these labs? I noticed that you do. I think the ball dropping was a lab, right? So how long is it? Just a week, or is it you give them 2 weeks? I mean, how much?
No, that one I usually do over 2 weeks.
Okay.
Although I have done it in a week before, and I don't know if you've ever heard of Dwayne Debian. You know Dwayne at all? He's at a junior college in Arizona. He won an AAPT award a few years ago for teaching. And the reason I'm bringing him up is he does this stuff, and he does every lab exercise or activity has a lab component, a spreadsheet computational component, although he predominantly uses GlowScript, and a analytical component. And he does it 1 week at a time. You only got 1 week to do this. The reason I'm bringing that up is he made a statement at his acceptance speech, and it's stuck with me ever since. He says, if we hold our students to a higher standard and you actually let them respond, it's rewarding. Interesting quote, huh?
Mm-hmm.
I mean, it sounds, and so when you look at my list, for instance, that list I showed at the very beginning, that looks very ambitious. And yes, it is if you've never done this before. But people like Dwayne look at it, and he's got junior college physics students nailing it on this kind of stuff, right? So that's always been a challenge for me, is try to press. Don't assume that your students won't be able to do this, right? Try it. I promise you I've made mistakes. There's nothing wrong, but you know, do it in single activities at a time. Don't try to implement this across the board, of course, right? So Brittany, I've got stuff I can share with you. But yeah, I do that over 2 weeks, but I have done it 1 week before. Any other comments or questions you have?
Yeah, I found something there I found useful was your idea of using the spreadsheet as a tool to teach programming, and in particular, the method where you're using you're homing in on the solution.
Yeah.
Because what I would have done was, for instance, when it was maybe you're talking about remembering the Pentium. I remember using 8087s and 8088 processors further back still, but I remember sort of teaching maybe students to program in a structured way using BASIC. And what I would do is I would use the Euler method to teach use the Euler method for for loops. You have definite steps. And then what I would do is put a while loop around that, half the time step, and keep iterating until the change from one step from one complete iteration to the next was less than a certain percentage or whatever there. So, what you were doing there in a sense is showing the idea of a for loop.
Yeah.
Then what you were doing afterwards, working with the homing in on a solution is showing the idea of a while loop. Keep going until it's good enough, essentially.
Right.
I thought it was interesting, your idea of using it to teach programming concepts.
Sure. I think, if you do start with a programming language, I think what you've just described is a good way to do it. You've got to get the students interacting with what the computer is doing, in my humble opinion, and you want them to be programmers. I mean, I want them reaching for MATLAB or C or whatever to do real number crunching. You're not going to do it. I mean, you can get away with a lot of data analysis on a spreadsheet, but I think the spreadsheet provides a way for them to visualize everything that they should understand and be doing, you know, in the programming language. So, you know, I don't have any physics education research level studies on how effective the spreadsheet is. I can only say anecdotally that I think it works wonders. So it's the thing I found that gets them into it and gets them confident the soonest, for whatever that's worth. All right. Well, you know, if there's anything else, I mean, I don't mind staying around a little while longer, or if not, we can call it a night. You know how to find me, I think. I've sent you emails, I think. So take advantage. Like I said, if we, you know, don't be offended if I have to schedule something a few days out or something like that. But I'm happy to meet with anybody if you think it would be worthwhile. I will send a follow-up message, including the locations of everything that I'm going to share with you. And so look for that. And then I'm going to leave it to you to contact me for if you want to get together. All right, how's that sound? Okay. All right. Well, I hope this has been worth something. You know, it's hard to squeeze a lot into a few hours. And I mean, you know, to go much more than this starts to risk burnout, of course. So, but we can continue as needed. All right. So in that sense, this isn't goodbye. All right.
Thank you so much.
Yep. You're welcome. So, okay.
Thanks, Kelly.
Yeah, you're welcome. It's good to see
Thank you.
those of you I know. It's great to see you all again. And those I've just met, it's great to see you too. And I hope we can interact more. Certainly on more of these webinars we do. All right. So, but also in other ways. Okay.
Appreciate all your time.
All right. Good night. And well, I'm not going to bid you drive safely because you're probably not driving, but good night and good luck. All right.
Last one out has to turn off the lights.
I can't figure out how to leave.
Actually, I don't either. Okay. I'm going to click the little red dot in the upper left corner. And I'm going to presume that's going to kill it. Bye-bye.
Okay. All right. Bye.